Last time, we showed the image of why we need an IR drop analysis in the power integrity PI. In this video, I'm going to show the image of why we need PI analysis with the package model in a SerDes system. To be clear, the package model should be extracted and available after the package design was done. Usually, it's very close to the chip tape-out date and might not have enough time to wait for the verification results. As we discussed the deterministic jitter DJ in the Why Jitter Budget video, we can verify the on-chip spice analysis with the IC packaging model in an S-parameter format to sign off the final jitter performance. In this spice test bench, not only the high-speed I/O package interface is connected to the on-chip output of the TX driver, but also the SerDes power pins VDDA and ground of the package model are connected to the on-chip supply bulb of the TX driver. Therefore, both SI and PI of the SerDes, including the package, should be verified here. As you can see, the eye width of the eye opening is not quite good, which is 70% UI due to the DJ only. Therefore, it's obvious the final sequence, including the chip package, would violate the 30% UI jitter specification in most protocols. Usually, the on-chip jitter of the TX driver should be good enough, and we could point out the finger at the package design for further improvement. As expected, with the revised package design, just replace all the S parameter of the package model and see if the DJ went down and get improvement. If not, just keep iterating the package design until the results are acceptably good. Fortunately, in this particular design experience with this packaging vendor, we can get a reasonably good DJ of 10% UI after a few package revisions, and we will have 12% RJ, and the total jitter is under 30% UI with an 8% UI margin. I hope our PI analysis image can show you that the initial package design might violate the jitter specification, even though the on-chip SerDes design was meeting the target with a good margin. This will give us an idea of the importance of performing the PI analysis with the package model. If there is a package design issue caught in the PI analysis, we could try to improve the package design to make the supply report drop from 40 mV to 15 mV, such that the DJ could go down from 30% UI to 10% UI dramatically. However, is the methodology of the PI analysis good or helpful? Good. Yes or no? The previous test bench, including both the SI and PI, would be necessary for the final design sign-off to make sure the package model in both the power and high-speed I/O pins are all good. But that's not a good approach in the debugging process, since we might not identify the root cause of the 30% UI DJ easily. Therefore, as we discussed in the YSI analysis video, we should apply the SI analysis itself along with the high-speed I/O package model. Then apply the PI analysis with the supply package model only. Is this test bench good enough? Think about the simulation time image for 5 seconds. Correct. Simulating the whole on-chip analysis is very time-consuming with the package model, and especially the package model will require several design iterations and optimizations. In addition, as we mentioned in the beginning, usually the package design phase is very close to the chip tape-out schedule. Unfortunately, we might not have enough time to wait for the long simulation time of the whole SPICE with package model. So, we must come up with a simplified on-chip power distribution network (PDN) modeling as follows. First, we can generate the current profile, for example, current versus time of the SerDes mission mode operation through the force clock simulation, which is mimicking the steady state to reduce the simulation time. Second, get the on-chip circuit impedance from any two applied supply voltage, V1 plus delta V, and the corresponding current, I1 plus delta I, such that the R on-chip equals delta V divided by delta I. Third, fill those precise value of the on-chip decoupling capacitors and impedance into the PDN. Lastly, connect the PDN with the power supply package model, and the test bench is ready to simulate. From this PI test bench image, what are the results you expect to get? Think about the supply voltage ripple for 5 seconds. Bingo! As we discussed in the white IR drop video, the current profile times the PDN should give you the supply voltage, including the static IR drop and dynamic IR drop shown here. Then we notice the supply ripple is 25 mV here. Can you evaluate if the supply noise of 25 mV is good or bad? Think about the delay or supply sensitivity for 5 seconds. Correct. We should translate the supply voltage in mV to the timing jitter in picosecond to evaluate the jitter specification properly. We've done the whole SPICE simulation including both PI and SI. For this simplified RX image, the data path is a differential CML buffer, so the delay or supply sensitivity is quite small, with roughly 0.02 picosecond per mV, and the 25 mV only translates to a 0.5 picosecond jitter, which is 0.5% UI of the 10 gigabit per second. On the other hand, the simplest sampling clock comes from the CMOS clock distribution path, and the delay sensitivity could be 0.4 picosecond per mV of the worst case. Therefore, the supply noise introduced jitter DJ of the clock could be 10 picosecond or 10% UI of 10 gigabit per second, which degrades the I width quite a lot. Therefore, in a good CMOS clock buffer design, we should either decrease the number of buffers or try to apply the low threshold voltage device to reduce the delay sensitivity to have better supply noise immunity. Lastly, although this supply noise introduced jitter is demonstrated at the RX, you still can apply a similar evaluation at the TX data and clock path together. Here is the summarized image of why we need a PI analysis with the package model in a SerDes system. Usually, the package design don't have any idea of the on-die current profile, which could have lots of switching noise left even though a few decoupling capacitors were added. Therefore, in our package design experience with one vendor, the substrate design in the supply routing was poor to cause the 40 mV ripple and 30% UI supply noise introduced jitter. After a few design revisions, not only the supply ripple can be reduced to 15 mV, but also the supply introduced jitter is decreased to 10% UI, which demonstrates the PI analysis with the package model is necessary and would require a few design iterations during the optimization phases. Unfortunately, package design may have a big delay and could be too close to the second tape-out schedule to have enough time to wait for a long simulation time. Therefore, the final sign of putting the whole SerDes, status, and the package model into the verification was not realistic, and that's only for the final design. During the debug or design application phases, we must create an on-chip PDN modeling and simulate the supply voltage ripple quickly. Then we could translate the supply noise ripple easily to the jitter of both the clock and data path in either the RX or the TX respectively. Hopefully, this PI analysis methodology would help us iterate the package design and identify the root cause quickly if a poor design was caught. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video with the people who may be benefit from it.